In this module, we have looked at the concept of polytomous regression. Polytomous regressions are a generalization of binomial regression models to the case when the outcome is not binary but consists of several categories. We have seen that when we have nominal outcomes, it is possible to consider something called multinomial regression, and we have seen basically with the help of an R example how this can be fitted. As you know, polytomous data can be either nominal categories or ordinal categories, and we have next considered the case of ordinal categories. We have defined something called proportional odds logistic regression, which, even though it makes strong assumptions about the data, leads to easily interpretable coefficients. And in a future module, we shall look at the theoretical underpinnings of polytomous regression modules. Learning objectives for this module. We will first define the multinomial distribution, which is a generalization of the binomial distribution. Next, we will define the concept of multinomial regression, which is an application of regression analysis to the case where the outcome is distributed as a multinomial family. Third, we shall define the concept of ordinal regression for the case where we have categorical data, but the categories are ordinal. And finally, we shall define proportional odds regression. All this will be done using illustrations in R. In this module, we shall rely on a case study taken from this wonderful book called Extending the Linear Model with R, which describes, as the title suggests, various extensions such as the GLM, the additive model, the mixed effects model, and non-parametric regression models, and so on. The book is by Julian Faraway, and there is associated R data and R code which is publicly available in the Faraway library in R. We shall look at detail at some of the derivations which he has used in his book, but it would be a very good exercise for you to look at the remainder of the applications which he has considered in great detail in his book. So to begin with, the multinomial distribution. As you all know, the multinomial distribution is an extension of the binomial distribution to the case where the response takes more than two values. So we assume that y is a random variable that can take one of a finite number of values. So let us say capital J values, and let Pij equal to the probability that yi is equal to j, I being the index for subjects. So we assume that we have n individuals, and for each individual the outcome has the multinomial distribution specified by the probabilities Pij j equal to 1 to capital J. Of course, we must have summation of Pij over j equal to 1 for every individual. Binary data is a special case when capital J is equal to 2. Now, in the case of binary data, we have considered two options, which is grouped and ungrouped data. Similarly, with multinomial data, we can consider grouped multinomial data and ungrouped multinomial data. It will not really make a difference to the regression analysis. Now, conditional on the total n, which of course may be 1, you all know that the multinomial likelihood is given by probability yi1 equal to small yi1 and so on up to probability yi capital J equal to small yi capital J is ni factorial by y1 factorial up to yij factorial into the product of pij's to the power yij's. The multinomial logic model. So when we define the concept of regression, the problem is to relate the outcomes to the covariates. To this extent, we assume that for each individual, we have not only measured observations on capital J dummy variables, yi1 to yij, but along with that, a set of covariates which can be summarized in a p vector xi, and our purpose is to relate the outcomes to the covariates. That is, we want to see how category membership is influenced by the covariates. So to begin with, let us define the linear predictor as we did for the binomial situation as eta ij equal to xi prime beta j. Now note that instead of having a single beta, we now have beta j's for j equal to 2 to j, and we further assume that eta I1 is equal to 0. So we relate the outcomes to the covariates using the equation log of pij by pi1 equal to xi prime beta j for j equal to 2 to capital J. So note that we must obey the constraint that summation over j pij is equal to 1, and this leads us to the simplification that pij is equal to e to the power eta ij by 1 plus summation j equal to 2 to j e to the power eta ij. Estimation and inference of this model can be done as before for the binomial situation using maximum likelihood and then associated inference methods developed for the case of maximum likelihood. Let us consider an application to the data NES96 included in the faraway library in R. The data is a subset of the 1996 American National Election Study, where for simplicity we consider the age, the education level, and the income level of the respondent. The response is the party identification of the respondent, which can be Democratic, Independent, or Republican. So note that we have a situation of nominal categories. So in this chunk of code, we have loaded the data and re-leveled the categories as Democrat, Independent, and Republican. The summary of the data shows that there are 380 Democrats, 239 Independents, and 325 Republicans. We use the summary on the income to get a summary of the income, and we can also look at the education of the respondents by using the table function. We first look at the relationship between the predictors and the response graphically. Now note that the response is at the individual level, and because we have individual specific covariates, we need to group the data to try and get these plots. You have already seen that this is necessary for the case when we have discrete outcomes such as category membership. So here we have cut the age and the income predictors into 7 levels and use the approximate midpoints to generate the plots given in this figure. So we can see that the proportion of Democrats falls with educational status, and it reaches a plateau for those who are college educated. You can see that the proportion of Republicans arises with educational level but also reaches a similar plateau. As income increases, we see that there is an increase in the proportion of Republicans and Independents and a decrease in the proportion of Democrats. Is to try and quantify these relationships and subsequently to see if the relationships can be considered to be statistically significant. In the chunk of code given on this slide, we are fitting a multinomial logic model. We do this using the multinorm function in R, and this is a part of the nnet package. The reason that the nnet package is used is that we need to use the optimization method from the neural net trainer in nnet to maximize the likelihood. Now, as with the logistic function, we can also do several model choices on the multinorm function. So, for example, we could use the function step to conduct a stepwise search method of the optimum set of covariates. On this slide, we have used standard likelihood based methods, which is the likelihood ratio, to compare nested models. So, for example, we can fit a model without education and then using the deviance command derive the deviances of the two models and use the p chi-square command to get an estimate of the significance. So, we can see from here that education is not significant relative to the full model. We can also look at the individual coefficients to try and get a better understanding of the relationship between the categories and the response. So, the intercept term models the probabilities of party identification for an income of 0. We can get this relationship using the chunk of code CC is C evaluated at the coefficients, and then using the predict function. The slope term represents the log odds ratio of moving from the baseline category of Democrat to Independent and Republican, respectively, for a unit change of $1,000 in income. So, we can see this more explicitly by predicting the probabilities for a range of incomes and then computing the log odds. We could also compare the predicted probabilities instead of the log odds to get a more intuitive picture. Now, as you know, there is a connection between the multinomial and the Poisson distribution, and it is possible to fit a multinomial logic model using a Poisson GLM. So, recall that if we have independent Poissons, then conditional on their total, the distribution of the data is multinomial. So, we can exploit this fact by declaring a factor that has a level for each multinomial observation of the data. We then treat the individual components as individual Poisson responses. For ungrouped data, this means that we have one response as 1 and the rest equal to 0. So, in the chunk of code given on this slide, we have set up these variables and also illustrated what happens for the first 4 rows of the data. The 3 Poisson responses corresponding to the 3 different party affiliations are next labeled, and we replicate the predictor. The reorganized data looks as has been displayed on this slide by using the head command. It gives the first 6 rows of the data. So, as with the contingency table models, the null model has only main effects and it has been fitted using the GLM function in R. The effect of income is modeled using an interaction with party affiliation. We can find the deviance from the 2 models, and we see that the deviance is the same as for the multinomial model. We could also look at the coefficients and see that they correspond. Let us next come to the case of ordinal multinomial responses. Now recall that categorical data can be nominal, that is, there is no ordering of the categories, or it can be ordinal. If you remember, then any method which can be used for nominal method could also be used for ordinal method. So we could continue to use multinomial regression, but we shall gain more information if we take into account that the categories are ordinal. So now we are assuming that we have capital J ordered categories, and that for individual I with ordinal response yi, Pij as before is probability of yi equal to j. Now because we have an ordered response, we will make one change, that is, we will now work with the cumulative probabilities gamma ij equal to probability of yi less than equal to j. Note that this is only meaningful because the categories are ordinal. Now the cumulative probabilities are of course non-decreasing and they are invariant to combining adjacent categories. Also gamma of capital J is equal to 1, so we only need to model gamma 1 to gamma j minus 1. Now of course in a regression setting, our main purpose is to relate the Pij's to the covariates, and we shall do this by using a link function g, which takes the form g of gamma ij is equal to theta j minus xi prime beta. Three common choices of g are the logic link, the probit link, and the complementary log-log link. This brings us to the question of which link is the appropriate and how to determine this empirically or conceptually for a given data set. Now we are somewhat helped by the fact that binary choice model, which we have seen to motivate logistic and probit regression for the case of binomial data, can also be generalized to the case of ordinal multinomial responses. So for example, if we assume that along with the y's and the x's, there is also an underlying, which is unobserved but underlying nevertheless, continuous variable z, and that yi equal to some little j is observed only if zi lies between two cutoffs, say theta j minus 1 and theta j. Then as with the binary choice model, if we look at the distribution of z, it is possible to show that this gives some indication for the proper choice of link. So for example, if z follows the logistic distribution, then it leads to gamma ij equal to exponential of theta j minus beta prime xi by 1 plus exponential theta j minus beta prime xi, which can be rewritten as log of gamma j xi over 1 minus gamma j xi equal to theta j minus beta prime xi, j equal to 1 to capital J minus 1. So this is a generalization of the logistic distribution to the case where we have ordinal responses. Now choosing the normal distribution for z would of course lead to a generalization of the probit model. Choosing an extreme value distribution would lead to the complementary log-log link. Now let us assume that log of gamma j x over 1 minus gamma j x is equal to theta j minus beta prime xj. This is the very common proportional odds model based on the logic link. It is called the proportional odds model because the relative odds for the event of y less than equal to j comparing x1 and x2 are given by gamma j x1 over 1 minus gamma j x1 divided by gamma j x2 over 1 minus gamma j x2 is exponential of minus beta prime x1 minus x2. So this is proportional to the difference between x1 minus x2 and does not depend on j. In this sense, this is an assumption of proportional odds. Of course, for any given data set, we would need to check whether the assumption holds, but this is an attractive model because unlike, for example, the multinomial model or several other competitors to the proportional odds model for ordinal responses, the coefficients and the results for this model can be easily interpreted. We can run an application of the proportional odds model using the Pol R function in R to our NES 96 dataset. The Pol R function is included in the mass library. So first we need to call the mass library and then we run the model Pol R of SPID on age plus education plus income. The syntax for the Pol R function is quite similar to the GLM function, and here we have calculated the deviance and the number of parameters for this model. Note that the proportional odds model uses fewer parameters, but it does not fit as well as the multinomial logit model. As we said, checking the assumption of proportionality is important. We can do this by computing the observed odds proportions with respect to the covariates, in this case income levels. So in this chunk of code we have computed the log odds difference between gamma 1 and gamma 2, and looking at the outcome, it is not immediately clear whether these can be considered constant. However, note that there is no trend. We can consider the interpretation of the fitted coefficients and see that the odds of moving from Democrat to Independent or Republican category or from Democrat or Independent to Republican increases by a factor of e to the power 0.01312, which is equal to 1.0132 as income increases by 1 unit. So note that income is measured in $1,000 units. So note that even though the models are different and the assumptions are different, the log odds are quite similar to those obtained in the multinomial logit model. We have spent quite some time looking at binomial regression. We have considered alternative regression models such as the logistic model, the probit model, and seen that other links such as the complementary log-log link or even the log link can easily be accommodated when we have binary outcomes. Now the situation sometimes arises that we have more than one outcome. So for example, when we are looking at smoking, instead of just looking at a binary classification of whether or not a subject is a smoker, it might be more meaningful to look at several categories. So for example, whether this person ever smoked, and if so, whether he is currently a smoker, was a smoker in his adolescence, was a chain smoker, and so on. In such situations, we have categorical data, and in this module, we will develop the technique of Polytomous regression for such data.